Hi, welcome to today's lesson. We're going to be talking about reactions of alcohols today. We briefly introduced alcohols in yesterday's lesson when we looked at the reactions of alkenes, and when we react an alkene with steam we get an alcohol, and today we're going to be looking at reactions that they undergo. Now before we do that, what I want you to do, a bit of retrieval. I want you to define these following terms. So what's an electron, what's a neutron, what's a proton, and what is an ion? Write in as much detail as you can and then we'll go through it. So pause the video now. Okay, so hopefully we got that an electron is a negatively charged particle found in the shells around the outside of the nucleus of an atom, and they are the smallest subatomic particle. We often say they have a mass of 0. Not entirely true, but it is very, 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 very small. Next one is a neutron. Now, neutron comes from the word neutral because they are neutrally charged. They have no charge. Again, these are found in the atom, but they are in the nucleus, and they have a relative mass of 1. So the mass isn't 1 gram, it is just of 1 in comparison to everything else. So proton, a nice easy way of remembering it, P for proton, P for positive. They're a positively charged particle found in the nucleus, and again, they have a relative mass of 1, which means they are roughly relatively the same size as a neutron, whereas the electron is much, much, much smaller. So what is crucial from this is that you know where these subatomic particles are, what their mass is, and what their charge is, because it affects a lot of things in both chemistry and physics that you understand this. So the last one then is an ion. What is an ion? It is a charged atom. So it's the atom as a whole that has become charged, and it's done that by gaining or losing electrons from its outer shell. So if it gains electrons, it is a negatively charged ion, and if it loses electrons, it is a positively charged ion. So make sure you've got those down, correct your answers if you got them wrong, and do learn those. They are very important for a lot of things in chemistry. So moving on to today's lessons, we said we're going to be looking at the reactions of alcohols. And before we do, we're going to be recalling the reactions of alkenes from yesterday. And that will help you to see where alcohols come from, where they get the structure from, and then we're going to look at the energy released by alcohols. You're going to need a calculator today. We are going to do a little bit of maths, and then we're just going to compare these reactions, the different reactions they undergo, and what happens. So this is from yesterday so that we can recall our reactions of alcohol. So what I want you to do, without looking, I want you to see if you can remember. So they're in a funny order, but we did this yesterday. So copy and complete each of these word equations. You don't need the symbols and you don't need the displayed formulas. It's just the general equation, because as you can see, we've got alkenes. We've not named any, it's just the general equation for each. So pause the video now before we go through the answers in a minute. Okay, so first one, alkene plus steam gives an alcohol, which I mentioned before, and that's the alcohol is what we're going to be talking about for the majority of this lesson. The next one, an alkene plus hydrogen gives you an alkane. So remember that hydrogen, that H2, attaches itself to the alkene at the double bond of the alkene where it opens up and the two hydrogens join, making it an alkane. So an alkene plus bromine will give you a dibromo compound. So it's a dibromo alkane. It joins on. So again, that double bond opens and the bromine attaches to the carbon each carbon either side of the double bond. And lastly, alkene plus oxygen. Hopefully you recognise that when you react something with oxygen, it is a combustion reaction. It's burning, so we get carbon dioxide and water. Remember, alkenes do not burn as cleanly as alkanes, and they don't release as much energy. That's why we don't use alkenes for fuels. We use them to make plastics and to react and do other things, because alkanes don't react, but alkenes aren't very useful for burning. Excellent. So we're going to keep going over those. We'll do them as retrieval in a few lessons time, just so that you're really confident on them. And we'll do a few more examples in retrieval as well, to make sure that you don't forget them, because they're very, very easy to forget, but they're also very important. So if we were in the lab now, we would be doing a nice practical about this, where we investigate the energy released by alcohols. I'm going to talk you through it. We're going to do the bit that comes after it. And when we go back to school, we will do the practical as well. So here is an example of an alcohol. Like I said, we touched on this yesterday, and all alcohols will have the similar structure. So as you can see at the end on that final carbon, you've got an OH. That is what makes an alcohol. They all end in oxygen with a hydrogen attached. Now, hopefully you can see from that displayed formula that you have 2 carbon atoms, which means that the start of it is F. So ethane, ethene, and this one is ethanol. Okay, this one, I want you to have a think of what the name might be with just 1 carbon atom. Okay, so 1 carbon atom, obviously we can't have it as an alkene, but the alkane will be methane. So this is methanol. So it's important that we understand how these fit in, not just into chemistry, but into life, because these have uses. Now, hopefully, you are aware of the term alcohol. At the moment, we're using hand sanitizers that have got alcohol in because they do work as good disinfectants. I'm sure you're all aware that alcohol is in alcoholic drinks. Now, that isn't any alcohol. Alcohol is the name of the family. So any compound that's got carbon and hydrogen with an OH on the end is an alcohol. The alcohol that is in drinks is ethanol, which is the one at the top left there. You wouldn't want, I mean, we're not drinking it anyway, but you wouldn't want to drink the methanol. It's very different. And then as you go down, propanol, butanol, and all the others, you have different properties, similar but different. So you wouldn't want to drink any alcohol. The drink is ethanol, because other ones we can use for fuels. So sometimes they're called biofuels. You can use ethanol as a fuel. It is highly flammable, so you have to be very, very careful. But the family of alcohols is the general term for any carbon compound where it's just made up of carbon and hydrogens, then you've got that OH group on the end. So if we take a look at some examples then, we can see the first one at the bottom, that's 1 carbon atom, so that would be methanol. The next one, 2 carbon atoms, so it's ethanol. Next one's the third one, 3 carbon atoms, propanol. And lastly, 4 carbon atoms, butanol. So the functional group in this situation is the OH on the end. Any reactions that alcohols undergo, it happens at that OH group. Okay, so the first one, methanol, if we look at that structural formula, CH3OH. Now, technically, it's CH4O. If we were just to put it all together, you've got 1 carbon, 4 hydrogens, and 1 oxygen, if we were just to not show the structure. But by putting the OH on the end like that, it shows you straight away that it's an alcohol. So technically CH4O is still right, but it doesn't help you understand the structure of it. So if you look at the black bit of that diagram, you can see you've got your CH3C with 3 hydrogens, and then you've got the O and the H on the end. By writing it that way, it helps you. So we move on to the next one, we can see we've got C2 and 5 H's, so C2H5, then OH. So we can split it up, and anything that ends in OH then we know is an alcohol, because if we'd have written C2H6O, it wouldn't have been as easy. But by showing it's the OH that's attached to the C2H5. So the next one, propanol. So you've got C3, because it's 3, H7OH, and finally butanol, C4H9OH. You don't need to be able to remember the formulas of these, because as long as you can draw them out and know that butanol means 4 carbon atoms, if I draw 4 carbon atoms, fill up the hydrogens apart from 1 on the end, you'll be able to work it out. Okay, so what we're going to do, and if we did this in the lab, we'd be doing the experiments, we're going to look at which fuel releases the most energy. And we do that using an experiment called calorimetry. And basically what a calorimeter is, and you can see it on the diagram, is where you use the fuel to burn and to heat up some water. And you measure the temperature change of that water. And using that equation at the top, you're then able to work out the energy that has been released by that fuel. So we're going to burn the alcohol, use the flame to heat the water. We're going to measure the temperature change, meaning you need to measure it at the start, measure it at the end, and then work out the temperature change. Now, to make this more comparable, you're going to burn each alcohol for the same amount of time. Now, if you look at the equation at the top, you've got energy transferred, and that's what we want to find out, is equal to the mass of the water heated. So it's not the mass of the fuel you use, we need that in a minute, but the mass of the water that's heated. So if we were to use 100 ml of water and say that's what we're going to do in the lab, 100 ml of water is 100 grams. So you're going to need that number in a bit. Then times by 4.2. Now I hope you recognise this equation as the equation for the specific heat capacity equation. So that's where 4.2 comes out of, because that's the specific heat capacity of water, and you times it by the temperature change. Okay, as you can see, there is a video link at the side. I've put that on ClassCharts. It's very useful because it shows a demonstration of this being carried out, so you can see exactly what we would do. When we do it in the lab, we're going to look at the specific control variables in this experiment, because it's really important, you know, of all the things that you've got to keep the same, make sure that your results are reproducible, because there are quite a few for this one. If you watch the video, it'll become a bit more clear, but we will go back over that when we return to school. So this would be your table. You've got your 3 alcohols down the left-hand side. You would measure the temperature of the water at the start, temperature of the water at the end, record the temperature change of the water, and you need to make a note of the mass of the fuel used. So you would weigh your spirit burner with your alcohol in at the start. You then burn it for 2 minutes, weigh it again at the end, and work out how much fuel you've used. You are going to need that number if we are to compare the fuels accurately. So if you've not used the same amount of fuel, you can't just calculate the energy and then say one is better than the other. You've got to do energy per gram. So imagine we've done this experiment and we've got these results. So the first thing I want you to do is copy down the table. It might be an idea to copy the diagram as well. And then I want you to calculate the temperature change of the water in each case. Okay, so now you've got 3 questions, well, 3 different things you need to do. So using this equation, the first thing I want you to do is calculate the energy released by each alcohol using that equation. So remember, we used the mass of water as 100 grams. So then all you need to do is times it by 4.2, times it by the temperature change that you've just calculated. Then you're going to use whatever your answer is to each of those, the three parts to question 1 for each of your fuels, and you're going to divide it by the mass of the fuel used. So you might want to go back to that table if you've not copied it down. So you get your answer from number 1 and you divide it by the mass of the fuel burnt, because that way, if we work out the energy per gram, we can compare the fuels a lot more easily. Because like I said, if we were just to say, oh, that one's released more energy, but they'd all used a different amount, we wouldn't be able to, it wouldn't make any sense, because one of them might have released more energy purely because more fuel was burned. So energy per gram is the best way to make a comparison. So then lastly, you want to write a sentence concluding which fuel releases the most energy per gram, so therefore which is the best fuel out of those 3 alcohols. So pause the video now. This will take you a little while and then we'll go through the answers. Okay, lovely. So starting off, obviously, like I said, you need to work out the temperature change of the water. So methanol was 12 degrees, ethanol was 19 degrees, and propanol was 28 degrees. Now notice how in the table itself, other than in the headings, I've not put my unit in the body of the table. I've just put the unit in the headings for each column. That is absolutely fine. Don't get into the habit of putting your units after every number. So you don't need to put 23 degrees C. The units are in the heading and that's where they belong. So you don't need to write anything other than your values in the table. So we're going to use the numbers then that we've just calculated, the temperature change of the water, to work out the energy transferred by each one. So we look at methanol, mass, which is 100, times C, which is the specific heat capacity, which is 4.2, times this change in temperature. So 100 times 4.2 times 12 gives 5,040 joules. And the next one, ethanol. So it's still 100 grams of water. We use the same amount each time. Specific heat capacity is still 4.2 times by 19 gives 7,980. And lastly, propanol. 100 times 4.2 times 28, giving 11,760. So that's question 1. That's the amount of energy released by each fuel. Now, like I said, we can't say which one's the best because they've all used a different mass of fuel. So the next question was to calculate the energy per gram. So I've got the same equations there, the answers to the last question, so because you will need to use that. So as we can see, methanol, the mass of the fuel used was 3.6. We can see that in the table. So if we do 5,040 divided by 3.6, energy per gram, 1,400 joules per kilogram. Oh, sorry, joules per gram, my bad, that is a typo there. Ethanol then is 7,980 divided by 2.8 gives 2,858 joules per gram, ignore the K, and propanol, 11,760 divided by 3.2 gives 3,675 joules per gram. And therefore, we can say that propanol is the best fuel as it releases the most energy per gram. So this is a very, very, very common experiment, and there's something that you would always do in the lab. And sometimes you see this in an exam paper as well. It's very common. It's also the way we test energy in food right at the beginning of the biology, where you burn food and use it to heat up some water. It's exactly the same method and the same equation. So it's very useful to know the method and know your control variables for this. So now we have investigated, or we've talked about the investigation. Do make sure you've watched that little video. We're now just going to look over what reactions alcohols undergo. So the best thing to do is just make a few notes as we're going along. Feel free to stop the video at any point, and then make sure that you answer the questions that will come up on the slides as we go. So here is on the left our alcohol. We've got methanol down there and we've got a beaker of water. Now, if we add an alcohol into water, it will dissolve. And they are soluble in water. Basically, even though it's another liquid, they won't form two separate solutions like oil would. They would dissolve together, they would mix. And they would form a neutral solution. Okay, so all alcohols dissolve in water to form a neutral solution. That's a really key point. You might want to make some bullet points of just key points about alcohols that you need to know. Okay, so if we've got our beaker filled with methanol then, if we add sodium to it, now sodium's a reactive metal. You'll have seen the demonstration when you add sodium to water, it fizzes, gives a couple of sparks, gives off a lot of energy. Now when you add sodium into an alcohol, the sodium will react and you get what we call a methoxide. Okay, so they react with sodium, you would still get hydrogen given off and a salt. So in this case, you've got sodium methoxide. If you put it in ethanol, you get sodium ethoxide, and so on. So you can see from there that you've got the hydrogen leaves the oxygen and the sodium joins on. So that's why hydrogen gas is given off. And then you've got your sodium, meth, and your oxygen that's no longer an alcohol because it's joined onto the sodium. So you would always get the metal and then the oxide of that, what would be then the alkane. Okay, so what is the pH of alcohol in water? I would write down the question or answer it in a full sentence and make sure you've got the answer. What do you observe when sodium is added? So what would you see? I've just told you what's given off, so what would you see? And then it says what gas is formed when sodium is added to an alcohol. So answer these questions and then we'll go through the answers. So what is the pH for alcohol in water? We said it was neutral. Our universal indicator paper that we put in went green, so it's pH 7. Look how that's written. It's a lowercase p and a capital H. Don't get those the wrong way around. We need to be really strict on ourselves with using the correct letters and cases for those. What do you observe when sodium is added to an alcohol? You would observe a gas given off. You would see bubbles. You would see maybe a bit of what looks like smoke, but it's not smoke because the gas is formed is hydrogen gas. So you would see that. Okay, just like when we add sodium to water, you get hydrogen. You get that in the same way here. Okay, so like we've just done, we've looked at this experiment. All alcohols burn in air, and just like when you burn an alkane or an alkene, you get carbon dioxide and water. You do in this case. So you've got the methanol plus oxygen, and oxygen being O2. So what happens is that oxygen breaks apart, joins on, and makes carbon dioxide and water. So what I want you to do then, I want you to turn this into the symbol equation. So write out the example ethanol plus oxygen for the word equation and then the balanced symbol equation underneath. You might need to go back to your notes to remember the formula for ethanol. So pause the video now and answer this question. Okay, so if we go through it, ethanol plus oxygen gives carbon dioxide and water. Like anytime we've got a complete combustion reaction. Symbol equation, so ethanol is C2H5OH plus O2 gives CO2 plus H2O, and then balancing it 3, 2, 3. So if we look at the start, we've got 2 carbon atoms, so we need 2 carbon atoms in the carbon dioxide. In total, we've got 6 hydrogens at the start, so we need a 3 in front of the water to make that 6 hydrogens. If we count up the oxygen atoms in the products, we've got 4 in the carbon dioxide, 3 in the water, which makes 7. This time it's a little bit easier than doing it for an alkane because we can take that 1 off there. So you've got 1, so you need 6 more, so it's 3 lots of O2. Okay, so obviously we've briefly touched on the uses, but they are used in biofuels, really important, and especially we're going to look at ethanol in a lot more detail of how it's created and how it's used in a few lessons' time. They're used in solvents, so things that might need to dissolve other things, a lot of cleaning products, like alcohols are very good for cleaning, it dissolves things really well. A solvent is something that dissolves something else, so it can be really, really useful. And obviously, as we know, it's used in drinks as well, but that's specifically ethanol, not just any of them. So in summary, this is the structure. The OH is the functional group. They dissolve in water to form a neutral solution. They react with sodium to make hydrogens and a salt, which would be sodium, and then the oxide. They burn in air, so they undergo combustion to produce carbon dioxide and water, and they are used for fuels, solvents in food and drink. So that's it for today. Do make sure you've made notes on each of those bits. Definitely get the diagrams, the displayed formulas down and the formulas so you know the difference between the first four: methanol, ethanol, propanol and butanol. Any questions, just drop me an email. Thank you very much.